Okie dokie. Hello everyone. We would continue to work on learning 3D graphics, and we are going to start working on the lighting map, which is kind of a simple thing, but has to be done. So let's do it. So previous one was materials, right? So let me copy materials to lighting map. Okay, I created 5 files. It's not very ergonomic to have so many files and just bounce between all of them, but I did not figure out what else we can do to improve the situation. Anyways, now I'm going to rename materials to lightning map. Lighting map. I think this is correct spelling. And so this one, I don't know, let's call it lighting map. I think it's fine for now. We can contract it anyways. And we need to update this one. Loading shaders, and I think we should be good to go. So let me compile. Okay, let's get in the debugger, run.h, and we do have lighting map here, so we can run it as is. And we do have same code what we had previously. Okay, now let's read the chapter.
In the previous chapter, we discussed the possibility of each object having a unique material of its own that reacts differently to light. This is great for giving each object a unique look in comparison to other objects, but still doesn't offer much flexibility on the visual output of an object. In the previous chapter, we defined a material for an entire object as a whole. Objects in the real world, however, usually do not consist of a single material, but of several materials. Think of a car. Its exterior consists of a shiny fabric. It has windows that partly reflect the surrounding environment. Its tires are all but shiny so they don't have specular highlights, and it has rims that are super shiny if you actually washed your car all right. The car also has diffuse and ambient colors that are not the same for the entire object. A car displays many different ambient/diffuse colors. All by all, such an object has different material properties for each of its different parts. So the material system in the previous chapter isn't sufficient for all but the simplest models, so we need to extend the system by introducing diffuse and specular maps. These allow us to influence the diffuse and indirectly the ambient component, since they should be the same anyways, and the specular component of an object with much more precision. Diffuse maps. What we want is some way to set the diffuse colors of an object for each individual fragment, some sort of system where we can retrieve a color value based on the fragment's position on the object. This should probably all sound familiar, and we've been using such a system for a while now. This sounds just like textures we've extensively discussed in the earlier chapters, and it basically is just that, a texture. We're just using a different name for the same underlying principle, using an image wrapped around an object that we can index for unique color values per fragment. In lit scenes, this is usually called a diffuse map. This is generally how 3D artists call them before PBR, since a texture image represents all of the object's diffuse colors. To demonstrate diffuse maps, we're going to use an image of a wooden container with a steel border one.
Okay, I'm going to also use wooden container. So let me take a screenshot. So we have a screenshot, and I'm going to edit it in GIMP. Okay, layer, crop to selection, image, crop to selection, image, scale image. Let's make it 256 by 256. 256 by 256. Low, no hollow. I don't know what all these scaling algorithms. I think it looks pretty good. So let's export it to projects, learning 3D graphics. Wooden container. Wooden container.png. Export. Export. Okay. Let's go back to the book.
Using a diffuse map and shaders is exactly like we showed in the texture chapter. This time, however, we store the texture as a sampler 2D inside the material struct. We replace the earlier defined vec3 diffuse color vector with the diffuse map. Keep in mind that sampler 2D is a so-called opaque type, which means we can't instantiate these types, but only define them as uniforms. If the struct would be instantiated other than as a uniform, like a function parameter GLSL, could throw strange errors. The same thus applies to any struct holding such opaque types. We also remove the ambient material color vector, since the ambient color is equal to the diffuse color anyways, now that we control ambient with the light. So there's no need to store it separately.
Okay, so we have material diffuse, material specular, and material shyness. Okay. Fragment shader. So we have only only diffuse, which is sampler 2D. Specular shininess. It's run out of water.
If you're a bit stubborn and still want to set the ambient colors to a different value other than the diffuse value, you can keep the ambient vec3, but then the ambient colors would still remain the same for the entire object. To get different ambient values for each fragment, you'd have to use another texture for ambient values alone. Note that we are going to need texture coordinates again in the fragment shader, so we declared an extra input variable. Then we simply sample from the texture to retrieve the fragment's diffuse color value.
Note we are going to need a texture coordinates again in the fragment shader, so we declared an extra input variable. Then we simply sample from the texture to retrieve the fragment's diffuse color. Text course. We frag position. Oh yeah, we have text coord. So we put text coord here. And we need to put text coord here as well. And we need to put text coord here, and v text coord equals a text coord 0. Okay. And go back to fragment shader. So now diffuse is material diffuse text coordinate. Texture material, I see. Texture material diffuse vec free. So it should go here, right? Like this. Texture material diffuse v text coord. I think that's right. And ambient is going to be exactly same. We take this one. Yeah, there is too many parentheses, right? Ambient. Okay. So we did this already. And
be sure to update the vertex attribute pointers of both VAOs to match the new vertex data and load the container image as a texture. Before rendering the cube, we want to assign the right texture unit to the material.diffuse uniform sampler and bind the container texture to this texture unit.
yeah, so now let's go to CPP file, and so I think I'm going to butcher brick texture. So let's bricks and let's call it crate. What is the name of the wooden container?
Wooden container.
Wooden container, and we would do wooden container.png. Material diffuse. So I think I should call this thing material diffuse. Material diffuse. Material diffuse. Oh, there is a material diffuse already. Okay. So we actually need to remove this thing. And let's go through bricks. So we'll get rid of this thing and put wooden container here. Wooden container. Like this. Wooden container. I think this is it. I'm not sure if I forgot anything or it's crashed, of course. 34 dot pin lighting map 3 4. So it says implicit cast from vec 4 to vec 3. I guess I should put XYZ here or RGB. So let's see. RGB. So this is the wrong texture. Interesting. Set texture material diffuse wooden container texture. I don't know. I do not understand the set texture shenanigan. Let look at examples. It's always zero. There is a there is a normal velocity previous corresponding. So S normal create uniform S normal. Oh, so it's specified. Okay. Sampler 2D. So it's specified like this, not like uniform. So this is the culprit. Okay. Lightning map. So instead of doing this, we should say sampler 2D material diffuse 1. So this would be 1. Okay. So I think this is the difference. And we should have a thing. Unexpected colon expansion as token 20. Sampler 2D. I think it's defined somewhere. Uniform sampler name. Texture 2D. So it's so I need to include BGFX shader. Normal and common. BGFX shader. So if I would do this include, would it help me? Failed to compile shader. It did not help. So probably I need to add the include D, right? it like this? I guess I need to delete the bin directory. I think it did run. Okay. So might be some... Nope, still crashing. Hmm. It's lower I. Okay. Make file. So we'll do lower I. Okay. Delete bins again. Oh, still crashing, but it is different errors. Undefined. Unexpected undefined. At token undefined. 60. Undefined variable. Hmm. Where is the fs underscore? Oh, so this one should be first line. Okay. So this line should be first line. So, and still smiley faces. So let's see. Material diffuse 1. And I'm doing set texture 1. As normal. Set texture 1. Would it help? Nope. What else? Smile texture, wooden container texture, material diffuse. So there is one more thing, how uniform is defined. Let's see. So this is as normal. So this is uniform. It's defined as a uniform sampler. There is a destruction for it. I don't know what's going on. So what I'm going to do is smile. I'm going to just get rid of smile. For now, and we will figure out what's going on later on. Okay. Light ambient. Oh, it's all these parameters or light ambient, light. Oh, light diffuse. Oh, we do have light diffuse, right? Light ambient, light diffuse, diffuse color, light color. So we are going to probably, let's remove this stuff. Let's make it 1. Super bright. Yep. So
Now, using a diffuse map, we get an enormous boost in detail again, and this time the container really starts to shine quite literally. Your container now probably looks something like this. Specular maps. You probably noticed that the specular highlight looks a bit odd, since the object is a container that mostly consists of wood, and wood doesn't have specular highlights like that. We can fix this by setting the specular material of the object to VEC 30.0, but that would mean that the steel borders of the container would stop showing specular highlights as well, and steel should show specular highlights. We would like to control what parts of the object should show a specular highlight with varying intensity. This is a problem that sounds familiar. Coincidence? I think not. We can also use a texture map just for specular highlights. This means we need to generate a black and white or colors if you feel like it texture one that defined the specular intensities of each part of the object.
so this is the image. I'm going to as well take the screenshot of it, copy, and plop it here, and then grab it like this, make the crop by selection, and then resize it to 256. No hello. Okay. And export a wooden container specular. Okay. So now we probably should do same thing. Lighting map.cpp. So I'm just going to search for wooden container and do wooden container specular. All right, and material specular. So we have wooden container specular, and this one should not light. This one should become sampler. Okay, and material specular. So I think this is what we want. Now we go to fragment shader and tell this one material specular 1. And from here we do texture material specular v text corn RGB, and I think that's it. I don't know if it did what it's supposed to do. Honestly, I have no idea. I don't think it did. Material shininess. Maybe I should set the shininess to 64 maybe. Now what just happened? Did it? Oh, I pressed Q, I guess. Oh my god, I keep pressing Q. No pressing Q. Yeah, I don't think it's doing what it's supposed to do. 128. No, I don't think it does. It does what it's supposed to do. So let's me swap this stuff, right? So let's see what would happen. Yeah, this is a right thing. So let me see what's wrong with the shader. So let me comment this thing out and put here vec free 1. Ah, there is a no shine. Light specular. Let's put to the max. What's going on? Okay, so this is shiny. So what is making it not good? So if I multiply by specular light, oh, this one is not. Let me see. Yeah, there is too many files. It's such a headache to juggle them. So light specular, spec 4 light. Oh, here we go. Okay, now they are shiny finally. Okay, so let me comment this thing out and uncomment this. I think it's too strong There is one value is too strong now, right? What it was? Yeah, this one. So now it's too strong. No. What is the name? Shininess. Yeah, let's do 64. I don't know. What's going on here? Let's look at the material specular. As I suspected. And why it is like this? Who knows? Nobody knows. Nobody knows. Ah. Oh, I commented too much. Look, I swapped them, literally swapped them up. So this is material diffuse, this is material specular, and for some reason it's sampling from the diffuse. And I don't know why. Material diffuse. Material specular. Yeah, so maybe there is some problems with the settings. Let's look at the main, right? OpenGL. Type, select render backend and render on account is default rendering backend will be specified appropriate to the platform. Render type, let's OpenGL, 2.1 plus. How to select adapter. So I set it to none, right? I set it to none. I do not understand. So what if I look at the what I'm looking, denoise deferred as normal, as color as normal, right? Denoise deferred combine. Let's find this file. GLSL. Interesting. There is only as normal, huh? Ah, because as color is not used. How about here? Albedo used. And normal also used. And gbuffer, right? So let's look at this file. This is looking. Maybe I should do texture 2D. I don't think it does any. Let's try it anyways. Oh! It did work? No, it did not work. I do not understand. BGFX textures example. Bump.cpp. Load texture, load normal, create uniform, sampler, set texture. So everything is as easy as it can be. And sampler to D, 0, 1. Maybe something in variant. Text chord, position normal. Vertex shader, text chords. I don't know. It just doesn't work. So I'm expecting. So let me show what I'm expecting. So what we can do for diffuse, I'm just going to put like a white color, right? So for diffuse, I'm going to put white color. Vec free 1, right? And I'm going to show what I'm expecting to see. Yeah, so I'm expecting to see okay, so for ambient we also put the white color. Vec 4 1. So okay. It's like a, you can see like a slight sheen of the wooden, but it is should be material specular, not the diffuse one. So both textures for some reason are same. I do not understand what I'm doing wrong. Lighting map.cpp. So this is the material diffuse, material ambient, material specular is a sampler. This is same. Material specular. Set texture 1. Set texture 0. I don't know what's going on. So like if I put this thing here, oh, I didn't do anything. Hmm. They both like what? I'm not uploading wooden at all. Oh, wait a second. So I should put, okay. So I should put this thing here. Right? So in this case, yeah, in this case it's doing what it's supposed to do. So like now we can see like border is a bit more shinier. Yeah, it's like here. It's like on extreme angles. Now we can see it is shinier. And I do not understand why it's doing this thing. Load texture. Maybe load texture is doing something funky. So like if I swap this thing. Theoretically it should not do any difference. Yeah, it did not do. So it's I do not know what's going on here. So let's try to maybe Claude to figure it out. Yeah, debugging again. Every time doing debugging. So project learning 3D graphics. Let's I'm just going to upload everything. Yeah, I'm going to keep make file as well. So no this. no this. Yeah. So let's drag and drop it here. You cannot add at most 20 attachment and message. Please select fewer attachments. How much you have? 58? There is no way there is a 58 files here. Anyways. Base example, basic lighting, camera, color, coordinate system, example cubes, get natives, hello triangle, lightning map, load program, load texture, main make file, materials, shaders, textures, transformations. I have an issue where the specular texture is the same as the diffuse texture.
I have an issue where the specular texture is the same as the diffuse texture.
Oh, is this culprit? Oh wait, this is creating. Material specular. Okay. So I probably should delete this. Would it help? Oh my god. AI did the thing. Wow. I mean, at least I kind of know what what symptoms lead to what, and probably I would know where to look, but it's kind of garbage, right? You did this mistake, and I would expect type system to help you. Anyways, we made the progress. Wow. AI was able to figure out. It's like in no time. Okay, let's continue. Sampling specular map. And we've got, okay, look at this. We done light clusters. Light clusters. Okay, we can close this, make the commit. So let's see at the changes. Okay, so lighting map. And if you want to follow along, I made the public repository. So this is all my code which I wrote, 17 commits, and this is my last commit, lightning map. So that's a thing. So let's read about light casters.
Light casters. All the lighting we've used so far came from a single source that is a single point in space. It gives good results, but in the real world we have several types of light that each act different. A light source that casts light upon objects is called a light caster. In this chapter, we'll discuss several different types of light casters. Learning to simulate different light sources is yet another tool in your toolbox to further enrich your environments. We'll first discuss a directional light, then a point light, which is an extension of what we had before, and lastly, we'll discuss spotlights. In the next chapter, we'll combine several of these different light types into one scene. Directional light. When a light source is far away, the light rays coming from the light source are close to parallel to each other. It looks like all the light rays are coming from the same direction, regardless of where the object in slash or the viewer is. When a light source is modeled to be infinitely far away, it is called a directional light, since all its light rays have the same direction. It is independent of the location of the light source. A fine example of a directional light source is the sun as we know it. The sun is not infinitely far away from us, but it is so far away that we can perceive it as being infinitely far away in the lighting calculations. All the light rays from the sun are then modeled as parallel light rays, as we can see in the following image. Because all the light rays are parallel, it does not matter how each object relates to the light source's position, since the light direction remains the same for each object in the scene. Because the light direction vector stays the same, the lighting calculations will be similar for each object in the scene. We can model such a directional light by defining a light direction vector instead of position vector. The shader calculations remain mostly the same, except this time we directly use the light's direction vector instead of calculating the light dire vector using the light position vector. Note that we first negate the light dot direction vector. The lighting calculations we used so far expect the light direction to be a direction from the fragment towards the light source, but people generally prefer to specify a directional light as a global direction pointing from the light source. Therefore, we have to negate the global light direction vector to switch its direction. It's now a direction vector pointing towards the light source. Also, be sure to normalize the vector, since it is unwise to assume the input vector to a unit vector. The resulting light dire vector is then used as before in the diffuse and specular computations. To demonstrate that a directional light has the same effect on multiple objects, we'll revisit the container party seen from the end of the coordinate system chapter. Also, don't forget to actually specify the direction of the light source. Note that we define the direction as a direction from the light source. You can quickly see the light's direction is pointing downwards. We've been passing the light's position and direction vectors as vec3s for a while now, but some people tend to prefer to keep all the vectors defined as vec4. When defining position vectors as a vec4, it is important to set the w component to 1.0 so translation and projections are properly applied. However, when defining a direction vector as a vec4, we don't want translations to have an effect since they just represent directions. Nothing more so then, we define the w component to be 0.0. Direction vectors can then be represented as vec4 0.2f minus 1.0f minus 0.3f 0.0f. This can also function as an easy check for light types. You could check if the w component is equal to 1.0 to see that we now have a light's position vector, and if w is equal to 0.0, we have a light's direction vector. So adjust the calculations based on that. Fun fact, this is actually how the old OpenGL fix functionality determined if a light source was directional light or a positional light source and adjusted its lighting based on that. If you'd now compile the application and fly through the scene, it looks like there is a sun-like light source casting light on all the objects. Can you see that the diffuse and specular components all react as if there was a light source somewhere in the sky? It'll look something like this. Point lights, directional lights are great for global lights that illuminate the entire scene, but we usually also want several point lights scattered throughout the scene. Point light is a light source with a given position, somewhere in a world that illuminates in all directions, where the light rays fade out over distance. Think of light bulbs and torches as light casters that act as a point light. In the earlier chapters, we've been working with a simplistic point light. We had a light source at a given position that scatters light in all directions from that given light position. However, the light source we defined simulated light rays that never fade out, thus making it look like the light source is extremely strong. In most 3D applications, we'd like to simulate a light source that only illuminates an area close to the light source and not the entire scene. If you'd add the 10 containers to the lighting scene from the previous chapters, you'd notice that the container all the way in the back is lit with the same intensity as the container in front of the light. There's no logic yet that diminishes light over distance. We want the container in the back to only be slightly lit in comparison to the containers close to the light source. Attenuation to reduce the intensity of light over the distance a light ray travels is generally called attenuation. One way to reduce the light intensity over distance is to simply use a linear equation. Such an equation would linearly reduce the light intensity over the distance, thus making sure that objects at distance are less bright. However, such a linear function tends to look a bit fake. In the real world, lights are generally quite bright standing close by, but the brightness of a light source diminishes quickly at a distance. The remaining light intensity then slowly diminishes over distance. We are thus in need of a different equation for reducing the light's intensity. Luckily, some smart people already figured this out for us. The following formula calculates an attenuation value based on a fragment's distance to the light source, which we later multiply with the light's intensity vector. Here d represents the distance from the fragment to the light source. Then to calculate the attenuation value, we define 3 configurable terms, a constant term kc, a linear term kl, and a quadratic term kq. The constant term is usually kept at 1.0, which is mainly there to make sure the denominator never gets smaller than 1, since it would otherwise boost the intensity with certain distances, which is not the effect we're looking for. The linear term is multiplied with the distance value that reduces the intensity in a linear fashion. The quadratic term is multiplied with the quadrant of the distance and sets a quadratic decrease of intensity for a light source. The quadratic term will be less significant compared to the linear term when the distance is small, but gets much larger as the distance grows. Due to the quadratic term, the light will diminish mostly at a linear fashion until the distance becomes large enough for the quadratic term to surpass the linear term, and then the light intensity will decrease a lot faster. The resulting effect is that the light is quite intense when at a close range, but quickly loses its brightness over distance until it eventually loses its brightness at a more slower pace. The following graph shows the effect such an attenuation has over a distance of 100. You can see that the light has the highest intensity when the distance is small, but as soon as the distance grows, its intensity is significantly reduced and slowly reaches zero intensity at around a distance of 100. This is exactly what we want. Choosing the right values, but at what values do we set those 3 terms? Setting the right values depend on many factors: the environment, the distance you want a light to cover, the type of light, etc. In most cases, it simply is a question of experience and a moderate amount of tweaking. The following table shows some of the values these terms could take to simulate a realistic sort of light source that covers a specific radius distance. The first column specifies the distance a light will cover with the given terms. These values are good starting points for most lights, with courtesy of Ogre 3D's Wiki 1.
Ogre 3D.
As you can see, the constant term kc is kept at 1.0 in all cases. The linear term kl is usually quite small to cover larger distances, and the quadratic term kq is even smaller. Try to experiment a bit with these values to see their effect in your implementation. In our environment, a distance of 32 to 100 is generally enough for most lights. Implementing attenuation to implement attenuation, we'll be needing 3 extra values in the fragment shader, namely the constant, linear, and quadratic terms of the equation. These are best stored in the light struct we defined earlier. Note that we need to calculate light dire again using position, as this is a point light, as we did in the previous chapter, and not a directional light. Then we set the terms in our application. We want the light to cover a distance of 50, so we'll use the appropriate constant, linear, and quadratic terms from the table. Implementing attenuation in the fragment shader is relatively straightforward. We simply calculate an attenuation value based on the equation and multiply this with the ambient, diffuse, and specular components. We do need the distance to the light source for the equation to work, though. Remember how we can calculate the length of a vector. We can retrieve the distance term by calculating the difference vector between the fragment and the light source and take that resulting vector's length. We can use GLSL built-in length function for that purpose. Then, we include this attenuation value in the lighting calculations by multiplying the attenuation value with the ambient, diffuse, and specular colors. We could leave the ambient component alone, so ambient lighting is not decreased over distance, but if we were to use more than one light source, all the ambient components will start to stack up. In that case, we want to attenuate ambient lighting as well. Simply play around with what's best for your environment. If you'd run the application, you'd get something like this. You can see that right now only the front containers are lit, with the closest container being the brightest. The containers in the back are not lit at all since they're too far from the light source. You can find the source code of the application at /src/2.lighting/5.2lightcasters./. Point light is thus a light source with a configurable location and attenuation applied to its lighting calculations. Yet another type of light for our lighting arsenal. Multiple lights in the previous chapters, we learned a lot about lighting in OpenGL. We learned about Phong shading, materials, lighting maps, and different types of light casters. In this chapter, we're going to combine all the previously obtained knowledge by creating a fully lit scene with 6 active light sources. We are going to simulate a sun-like light as a directional light source, 4-point lights scattered throughout the scene, and we'll be adding a flashlight as well. To use more than one light source in the scene, we want to encapsulate the lighting calculations into GLSL functions. The reason for that is that the code quickly gets nasty when we do lighting computations with multiple light types, each requiring different computations. If we were to do all these calculations in the main function only, the code quickly becomes difficult to understand. Functions in GLSL are just like C functions. We have a function name, a return type, and we need to declare a prototype at the top of the code file if the function hasn't been declared yet before the main function. We'll create a different function for each of the light types: directional lights, point lights, and spotlights. When using multiple lights in a scene, the approach is usually as follows. We have a single color vector that represents the fragment's output color. For each light, the light's contribution to the fragment is added to this output color vector, so each light in the scene will calculate its individual impact and contribute that to the final output color. A general structure would look something like this. The actual code will likely differ per implementation, but the general structure remains the same. We define several functions that calculate the impact per light source and add its resultant color to an output color vector. If, for example, 2 light sources are close to the fragment, their combined contribution would result in a more brightly lit fragment compared to the fragment being lit by a single light source. Directional light, we want to define a function in the fragment shader that calculates the contribution a directional light has on the corresponding fragment, a function that takes a few parameters and returns the calculated directional lighting color. First, we need to set the required variables that we minimally need for a directional light source. We can store the variables in a struct called dirLight and define it as a uniform. The struct's variables should be familiar from the previous chapter. We can then pass the dirLight uniform to a function with the following prototype. Just like C and C++, when we want to call a function in this case inside the main function, the function should be defined somewhere before the caller's line number. In this case, we'd prefer to define the functions below the main function, so this requirement doesn't hold. Therefore, we declare the function's prototypes somewhere above the main function, just like we would in C. You can see that the function requires a dirLight struct and 2 other vectors required for its computation. If you successfully completed the previous chapter, then the content of this function should come as no surprise. We basically copied the code from the previous chapter and used the vectors given as function arguments to calculate the directional light's contribution vector. The resulting ambient, diffuse, and specular contributions are then returned as a single color vector.
Yeah, so there is some example with multiple lights. I do not remember where is it. Third party BGFX. Not such file or directory. Where I should go? Runtime? Okay. So zero one cube 02 03 04 05 06 So there is a multiple lights, I think. So let's look at the sample example 06. Num lights 4. Num lights, so yeah, it's U light radius. Oh, it just provides the index and you just okay. So it's the function is not taking anything, it just takes the index and then it's ugly, but whatever. Just make it work, right? Okay, let's go back to reading. Review.
Congratulations on making it this far. I'm not sure if you noticed, but overall the lighting chapters, we learned nothing new about OpenGL itself aside from a few minor items, like accessing uniform arrays. All of the lighting chapters, so far, were all about manipulating shaders, using techniques and equations to achieve realistic lighting results. This again shows you the power of shaders. Shaders are extremely flexible, and you witnessed firsthand that with just a few 3D vectors and some configurable variables, we were able to create amazing graphics. The last few chapters you learned about colors, the Phong lighting model that includes ambient, diffuse, and specular lighting, object materials, configurable light properties, diffuse and specular maps, different types of lights, and how to combine all the knowledge into a single fully lit scene. Be sure to experiment with different lights, material colors, light properties, and try to create your own environments with the help of a little bit of creativity. In the next chapters, we'll be adding more advanced geometry shapes to our scene that look really well in the lighting models we've discussed.
So loading models.
In all the scenes so far, we've been extensively playing with our little container friend, but over time, even our best friends can get a little boring. In bigger graphics applications, there are usually lots of complicated and interesting models that are much prettier to look at than a static container. However, unlike the container object, we can't really manually define all the vertices, normals, and texture coordinates of complicated shapes like houses, vehicles, or human-like characters. What we want instead is to import these models into the application, models that were carefully designed by 3D artists in tools like Blender 1, 3ds Max 2, or Maya 3. These so-called 3D modeling tools allow artists to create complicated shapes and apply textures to them via a process called UV mapping. The tools then automatically generate all the vertex coordinates, vertex normals, and texture coordinates while exporting them to a model file format we can use. This way, artists have an extensive toolkit to create high-quality models without having to care too much about the technical details. All the technical aspects are hidden in the exported model file. We, as graphics programmers, do have to care about these technical details though.
TK agent, hello.
It is our job to parse these exported model files and extract all the relevant information so we can store them in a format that OpenGL understands. A common issue is that there are dozens of different file formats where each exports the model data in its own unique way. Model formats like the wavefront.oj4 format only contains model data with minor material information like model colors and diffuse/specular maps, while model formats like the XML-based collada file format 5 are extremely extensive and contain models, lights, many types of materials, animation data, cameras, complete scene information, and much more. The wavefront object format is generally considered to be an easy-to-parse model format. It is recommended to visit the wavefront's wiki page at least once to see how such a file format data is structured. This should give you a basic perception of how model file formats are generally structured. All by all, there are many different file formats where a common general structure between them usually does not exist. So if we want to import a model from these file formats, we'd have to write an importer ourselves for each of the file formats we want to import. Luckily for us, there just happens to be a library for this. A model loading library, a very popular model importing library out there, is called a SIMP, that stands for Open Asset Import Library. A SIMP is able to import dozens of different model file formats and export to some as well by loading all the model's data into a SIMP's generalized data structures. As soon as a SIMP has loaded the model, we can retrieve all the data we need from a SIMP's data structures. Because the data structure of a SIMP stays the same, regardless of the type of file format we imported, it abstracts us from all the different file formats out there. When importing a model via a SIMP, it loads the entire model into a scene object that contains all the data of the imported model/scene. A SIMP then has a collection of nodes where each node contains indices to data stored in the scene object, where each node can have any number of children.
I actually was loading models. Was it an API? Where is it? Media, Mika, Kansas. No. Texas project. Oh. Assets. Server client. Load model. File name. Oh, yeah, I was using a SIMP. Same library. Okay. Building a SIMP. So I'm just wondering if I include this stuff, would it work or not? 19 as SIMP. So let's create new class as SIMP, or new example, I don't know how to call it, as SIMP. New sample con. So now let's rename lighting map SIMP. Okay, let's compile. What's going on here? And run a simp. Arithmetic exception. What did I do wrong? Arithmetic exception. I see what's going on. So I need to fix it. Base example. So the problem is with this map. So what we need to do, we cannot do this examples map. So we need to have static get map, and we would return get examples, right? And we would return the map, which would be like this. Get examples map, I guess. Let's call it get examples map. And we would do auto examples equals get examples map. Like this. And now we need to implement it, and we would implement it here. Static temp return temp. Like this. I think we should be good now. Yeah, we good. And example is working. Okay. So now let's see if I integrated a simp. So let's get the code model loader. Let's see if I put that stuff here. A simp importer file not found. Yeah, there is no simp. So let's look.
You can download a simp from their download page 1 and choose the corresponding version. For this writing, the simp version used was version 3.1.1. It is advised to compile the libraries by yourself, since their precompiled libraries don't always work on all systems. Review the Creating a Window chapter if you forgot how to compile a library by yourself via CMake. A few issues can come up while building a simp, so I'll note them down here with their solutions in case any of you get the same errors. CMake continually gives errors while retrieving the configuration list about DirectX libraries missing, messages like
I'm wondering how did I do it here? Or it might be part of Unreal Engine, maybe. Nothing. Oh, I misspelled it. And I have a pre-built version, so there is a libs. Interesting. Did I do this thing on Windows? This is why, probably, yeah. Yeah, there is no Linux stuff. So this one is not going to work on Linux because there is always Windows shenanigan. The lib. So there is a lib and there is include. Let's see. What's going on? For redeem model import library utilities. So version 5.2, dependencies, libsimp, installed files. The list of installed files only available for installed packages. Interesting. Libsimp. Why there is no libsimp? That's odd. Huh. Oh, libasynth is here. Okay, let's see. Installed file. So it has SO file, but we need libasynth dev, I guess. So let's install it. And change Spotify client. Okay, apply. So let's see what files are here. Does it have package config? Oh, look at this. Beautiful. I love. Then it's just normal library which has like a header files, package config, and that's it. Oh, it even has CMake stuff, but who cares? It has package config. So I'm going to integrate it with my Codel build tool. So we're going to put it here. It's package config. The name is simp, and we just need to have a list of include files. Copy, paste. Let me look what package config returns. So package config dash c flags simp. It returns nothing. Leaves, right? Oh my god, that's such a beautiful library. So it returns nothing, so it means we need to do it this way. I'm inclining, I mean, we can, because it's not going to collide with anything, so we can just keep it as this. Rosemary, best viewers. Rosemary, you're going to be banned. Bloop. And it just comma separated stuff. So let's do it like this, and like this. So we put like here like this, right? So we can even come on. How many spaces? 1, 2. Of course, 2 spaces. It's only 2 spaces, no more. 2 spaces. Okay. Status. Simp includes and nothing. It's package config. Package config is good. Add a simp library.
Add the assimp library.
Bloop. Bloop. And so So let's close everything. And I think I do not know if I just remove this thing. Anyways, I think it would need to rebuild everything. So I could just delete the whole thing. Anyways, redefinition of a so I should, okay, so we should call it differently. A simp tutorial tutorial. So now we need to update this stuff. Sim tutorial. Compiled. Beautiful. So let's we compiled it. We didn't need to do this stuff. Look, I mean, this is not this stuff. Where is it? I don't know. I never use CMake, so I have no idea. With a sim, we can load many different models.
With a simp, we can load many different models into the application, but once loaded, they're all stored in a simp's data structures. What we eventually want is to transform that data to a format that OpenGL understands so that we can render the objects. We learned from the previous chapter that a mesh represents a single drawable entity, so let's start by defining a mesh class of our own. Let's review a bit of what we've learned so far to think about what a mesh should minimally have as its data. A mesh should at least need a set of vertices where each vertex contains a position vector, a normal vector, and a texture coordinate vector. A mesh should also contain indices for index drawing and material data in the form of textures, diffuse/specular maps. Now that we set the minimal requirements for a mesh class, we can define a vertex in OpenGL. We store each of the required vertex attributes in a struct called vertex. Next to a vertex struct, we also want to organize the texture data in a texture struct. We store the ID of the texture and its type, for example, a diffuse or specular texture. Knowing the actual representation of a vertex and a texture, we can start defining the structure of the mesh class.
Okay. I guess we put everything in unnamed namespace. Texture. Mesh. Stat string. Stat vector. Oh, they have a shader. It's not called shader, it's called program handle. Program handle. position normal, text quotes. So layout is same, so I can leave the layout.
As you can see, the class isn't too complicated. In the constructor, we give the mesh all the necessary data, we initialize the buffers in the setup mesh function, and finally draw the mesh via the draw function. Note that we give a shader to the draw function. By passing the shader to the mesh, we can set several uniforms before drawing like linking samplers to texture units. The function content of the constructor is pretty straightforward. We simply set the class's public variables with the constructor's corresponding argument variables. We also call the setup mesh function in the constructor.
Vertices, indices, textures. Vertices, indices, textures, set up mesh. Okay, setup mesh, VO, VBO, EBO, vertex, vertex array, vertex buffer, and what is EBO? EBO. Element buffer object. So I'd like to discuss then rendering vertices that element.
There's one last thing we'd like to discuss when rendering vertices, and that is element buffer objects abbreviated to EBO. To explain how element buffer objects work, it's best to give an example. Suppose we want to draw a rectangle instead of a triangle. We can draw a rectangle using two triangles. OpenGL mainly works with triangles. This will generate the following set of vertices. As you can see, there is some overlap on the vertices specified. We specify bottom right and top left twice. This is an overhead of 50%, since the same rectangle could also be specified with only 4 vertices instead of 6. This will only get worse as soon as we have more complex models that have over 1,000s of triangles where there will be large chunks that overlap. What would be a better solution is to store only the unique vertices and then specify the order at which we want to draw these vertices in. In that case, we would only have to store 4 vertices for rectangle and then just specify at which order we'd like to draw them. Wouldn't it be great if OpenGL provided us with a feature like that? Thankfully, element buffer objects work exactly like that. An EBO is a buffer, just like a vertex buffer object that stores indices that OpenGL uses to decide what vertices to draw. This so-called index drawing is exactly the solution to our problem. To get started, we first have to specify the unique vertices and the indices to draw them as a rectangle.
Draw object in the choice object provides a array function that's draw primitive using the currently active shader, the previously defined vertex attribute configuration, and with VBO vertex data. Find vertex array. Okay. So initialize Initialization. Step mesh, bind vertex array, bind buffer, buffer data, vertices, indices, position vertex normals, vertex texture coordinates. Okay, setup mesh. Render data. VIO, VBO, EBO. Vertices. So we actually have VBH and IBH only. So I think we would stick with that. So I'm going to stick with that. Okay, and have I tried Vulkan before? I never tried Vulkan to program in Vulkan. It's quite involved to, you know, how many lines? 300 lines for just a triangle. And essentially, I decided to go with BGFX because apparently it's can as a backend have a Vulkan. So if I want to, I can switch to Vulkan backend, and it's just with some tweaking would work. But also it's supports DirectX backend or Metal or Web GL and all this shenanigan. Yeah. So why not? And I guess step mesh is going to be quite simple. So we just vertices, data size, and I guess we should put all this stuff below here. Yeah, look at this. And instead of try list, we would say indices, right? Indices. Cool. And indices here uin16. Let me make sure. It is uin16. 16. Okay, so as you can see, this is the example in OpenGL, and this is in BGFX. So I think there is a way less boilerplate code. I guess I will move layout here and move it here, vertex, so delete that thing. Vertex here, so we do not need any of these anymore. Nah, let's continue.
The code is not much different from what you'd expect, but a few little tricks were used with the help of the vertex struct. Structs have a great property in C++ that their memory layout is sequential. That is, if we were to represent a struct as an array of data, it would only contain the struct's variables in sequential order, which directly translates to a float actually byte array that we want for an array buffer. For example, if we have a filled vertex struct, its memory layout would be equal to. Thanks to this useful property, we can directly pass a pointer to a large list of vertex structs as the buffer's data, and they translate perfectly to what GL buffer data expects as its argument. Naturally, the sizeof operator can also be used on the struct for the appropriate size in bytes. This should be 32 bytes, 8 floats, 4 bytes each. Another great use of structs is a preprocessor directive called offsetoff_sm that takes as its first argument a struct and as its second argument a variable name of the struct. The macro returns the byte offset of that variable from the start of the struct. This is perfect for defining the offset parameter of the GL vertex, a trib pointer function. The offset is now defined using the offsetoff macro that in this case sets the byte offset of the normal vector equal to the byte offset of the normal attribute in the struct, which is 3 floats and thus 12 bytes. Using a struct like this doesn't only get us more readable code, but also allows us to easily extend the structure. If we want another vertex attribute, we can simply add it to the struct, and due to its flexible nature, the rendering code won't break. Rendering the last function we need to define for mesh class to be complete is its draw function. Before rendering the mesh, we first want to bind the appropriate textures before calling GL draw elements. However, this is somewhat difficult since we don't know from the start how many, if any, textures the mesh has and what type they may have. So how do we set the texture units and samplers in the shaders? To solve the issue, we're going to assume a certain naming convention. Each diffuse texture is named texture diffuse n, and each specular texture should be named texture specular n, where n is any number ranging from 1 to the maximum number of texture samplers allowed. Let's say we have 3 diffuse textures and 2 specular textures for a particular mesh. Their texture samplers should then be called
Texture diffuse, 1, 2, 3, specular, okay.
By this convention, we can define as many texture samplers as we want in the shaders up to OpenGL's maximum, and if a mesh actually does contain so many textures, we know what their names are going to be. By this convention, we can process any amount of textures on a single mesh, 20.2 rendering 163, and the shader developer is free to use as many of those as he wants by defining the proper samplers. There are many solutions to problems like this, and if you don't like this particular solution, it is up to you to get creative and come up with your own approach. The resultant drawing code then becomes
Okay, texture diffuse, texture specular, and materials. Name texture diffuse number set material name number bind texture. So we need to have a bit different system, because I do not know how this. I think they did implement this stuff. Setting uniform values. Set float I. What the heck is this? Why it set float I? Doesn't make any sense.
Now, it is time to get our hands dirty with a simp and start creating the actual loading and translation code. The goal of this chapter is to create another class that represents a model in its entirety, that is, a model that contains multiple meshes, possibly with multiple textures. A house that contains a wooden balcony, a tower, and perhaps a swimming pool could still be loaded as a single model. We'll load the model via a simp and translate it to multiple mesh objects we've created in the previous chapter. Without further ado, I present you the class structure of the model class.
Whatever. So we have model class.
The model class contains a vector of mesh objects and requires us to give it a file location in its constructor. It then loads the file right away via the load model function that is called in the constructor. The private functions are all designed to process a part of a simp's import routine, and we'll cover them shortly. We also store the directory of the file path that we'll later need when loading textures. The draw function is nothing special and basically loops over each of the meshes to call their respective draw function.
So this is not a shader, it's BGFX program handle. Okay. Simp importer scene and post process. Importer scene and post process, exactly what I have here. We're calling load module. So is it in the constructor, I guess? Oh, it's in the function load module. Load model, right? So this part. Okay. Ow. I'm just going to copy paste the code. Process known. Oh, it's just a freestanding function. Is it freestanding? Oh, no, it's not freestanding function. So process node is here. Wherever I don't care. I did it once. It's not that hard. Material index. What? Why there is a...
Translating an AI mesh object to a mesh object of our own is not too difficult. All we need to do is access each of the mesh's relevant properties and store them in our own object. The general structure of the process mesh function then becomes: processing a mesh is a three-part process. Retrieve all the vertex data, retrieve the mesh's indices, and finally retrieve the relevant material data. The process data is stored in one of the three vectors, and from those a mesh is created and returned to the functions caller. Retrieving the vertex data is pretty simple. We define a vertex struct that we add to the vertices array after each loop iteration. We loop for as much vertices there exist within the mesh retrieved via mesh mnum vertices. Within the iteration, we want to fill this struct with all the relevant data. For vertex positions, this is done as follows. Note that we define a temporary vec3 for transferring a simp's data to. This is necessary as a simp maintains its own data types for vector, matrices, strings, etc. And they don't convert that well to GLM's data types.
So normals and UV. Indices, materials. Load materials. Come on, let's do this thing. So there is a link to the model. Anyways, so process mesh. Let's do it. Copy. So indices are u in 16. Okay, so vertices, pushback, and then it's returns mesh. Okay, mesh m vertices I. Pushback vertex position normal text coordinate. Position normal text coordinate. Dot position. Oh, it's a capital P. Oh my god. Position equals glm avec free mesh m vertices ix y z position dot normal equals xyz m normals mesh m normals dot x. This is glm avec free y z text chords equals glm vec2 mesh texture chords 0 0 I dot x. Y does the mesh contain texture coordinates? Oh, so I need to make the check. So indices, copy, paste. Oh. Okay, indices are taken care, and material. Hmm. I'm just going to copy paste all this code. I know, I don't think I would. I kind of running out of steam, and maybe I should do it later. Texture from file. So there is a code to load texture. Load texture. And PGFX texture handle. So texture ID, it's this one. No matching function to call load texture. What? It's here. Why it cannot call load texture? Hmm. Oh, it's I see. So I need to convert this string simp c string. So dot c star texture path string type. I guess it's a type name. Why path is missing? We need to run this thing in the destructor. So Set index buffer, set vertex buffer. Set index buffer, set vertex buffer. And remove this. Okay, it's compiling. Uh, yeah. Anyways, I think I will continue later on that. Kind of tired. There is a little bit, but yeah, I'm tired. I'm not going to push, and this is quite a big topic, and I was thinking I could do it. We will continue on this thing. Okay, thank you for watching, and see you next time. Bye.